Hello, my structural analysis friends. Welcome back. In this lesson, we're going to be talking about tributary areas. We spent some time previously determining magnitudes of dead loads and live loads and wind and even snow, and always converted those calculations to some sort of pounds per square foot or PSF magnitude. In this lesson, we're going to discuss how do I convert that PSF pressure into an actual load on a building. And so that's the plan. So without further ado, here we go. So to start taking pressures from loads and applying them to a structure, you have to have some sort of framing diagram at your disposal. Okay, now what I've shown here is a typical plan view diagram. Now it's an irregularly shaped structure, but that's part of what the exercise is all about. And so if you say you have a dead load of 50 pounds per square foot or a live load of 100 pounds per square foot or whatever the numbers are, that PSF units that's on that indicates that it is an area load, that it's related to the area on which it's acting. So, a 1 by 1 square foot area anywhere here, here has the same value as if one here has the same value as one that's over here. It's still the same basic area. What we need to look at is how do we design the members or the structural framing to support those loads, and that's where these tributary areas will start to come in. Now, this can be done, for most of the time, it's a vertical load. We're dealing with plan view diagrams, which comes from either the architectural drawings or from the structural framing if you haven't already made that. But the same approach also works for, horizontal applied pressures such as wind or seismic effects or anything like that, as long as you have the framing of the surface on which the load is acting. Now, normally what's done for plan views is we assume that since, most buildings have some sort of concrete slab applied to it, that the loads are acting on top of that slab, and the slab is being carried by the framing. What we're after in this case is figuring out what are the loads that would show up on the framing itself. Now, when you get to slab design in your concrete class, you'll handle the slab itself a little bit differently. But for us, we're thinking more of like the structural steel or even the concrete members below that are holding it part of that main structural system, if you will. So with our structural framing diagram laid out here for us, you can see I have some column grid lines that are defined that help me locate the columns, and we'll work on figuring out those locations and some of these dimensions in a later video. But for applying these PSF loads, whether they're from dead load or live load or what have you, we have to kind of look at, what area is responsible for each of the members. So for, say, an interior beam up in this bay, we would look at how much of the load is acting on him, and what is the shape of that load pattern? How do we convert that PSF to something that we can design for? If you remember back when you were looking at like statics or early structures problems, the loads on a beam are typically measured in something like pounds per foot or newtons per meter. Okay, so we've got to get that units of pounds per square foot converted over somehow, and that's where these tributary areas and these tributary widths will start to come into play. But we do know that the load on this beam will be different than the one on this one, and the load on this girder is different than the one on this, and the load on this column is different than any other column in the building, just because this structure is so irregularly framed. And there's some interesting things that happen around openings as well that we'll talk about in a later video as we move through this. So as we're trying to figure out the shapes of the areas associated with each member, there's one important point that we have to kind of take a look at, and that it has to do with the type of framing that we're dealing with. Okay, now if I flip over to some diagrams I found, one of the concepts that's always kind of running around in the back of our mind is, are we talking about flush framing or are we talking about non-flush framing? Okay, and so there's a couple of different categories that exist on this, and this has to do with, in this case, this is a girder and this is a beam. The one on the bottom is a girder, and a girder being what connects the columns, say, and we come back and look at this. This would be a girder, goes from column to column. This could either be a beam or a girder, but usually a girder is a member that holds up other pieces. So the guy that's going from A to B on this picture, okay, is supporting this beam and this beam and this beam and this one and so forth and so on. Okay, so that's what makes him a girder. It's basically, it's a primary type member. Okay, but what we're interested in is how's the framing between this guy and this? How is this guy connected, this beam here, connected to the girder on which he sits? And it could be different for each end, but that's what we're talking about when we're talking about the framing type, okay? And so there's a couple of classifications we need to kind of spell out. Okay, the two most common ones are non-flush and flush. Okay, so a non-flush framing is when you have a girder and the beam that's framing into it sits directly on top of this. Okay, this is by far the easiest of the connections to make because normally I place the girder in place on the when I'm building the structure, and then this beam just sits directly on top. Okay, as opposed to, say, one of the flush diagrams, and there's a couple of different ways to do this. This is kind of a full depth flush. This is a partial depth flush, but you'll notice that on both of these, this picture and this one over here, you'll notice that the flat surface on the girder and the beam are all matching. Okay, it's the same elevation. That so if I go and I pour a slab onto a flush framing system, the girder and the beam both will start to help us. I lost my train of thought there. The girder both will help contribute to supporting that particular slab. Okay, now there is something called a semi-flush, which is kind of, it's not flush on top or bottom. It's kind of held down. And this one's unusual because in this case these are the beams, but it's the girder that carries the weight of the slab. Right? Because think about it, a slab travel. If there's another beam happening over here, the slab spans between these beam members. Okay, and so you're asking yourself, is the girder helping to hold the load? And that will dictate the changes in our particular areas. All right, so if we come and we kind of look at this, so those are our definitions: non-flush and flush, and then of course semi-flush is kind of a reverse, but we don't do a lot of this in structures, especially when concrete slabs are involved. So for the purposes of this class, we won't focus on that one, but these two we'll definitely kind of be talking about. Okay, so if we look at, say, for a non-flush, and here's where the differences are. So non-flush framing is the case where I have a beam running over the top of the girder. Okay, and so if I look at just kind of a typical regularly framed rectangular section on this, and I look at that girder that goes from what would be A to B, and if I see if we can zoom this in a little bit so you guys can see it. All right, so if we're looking at trying to figure out so we're looking at this girder that is what we would call AB2, so it's between A and B on column line 2 would be this girder that's spanning from here to here. And if it's a non-flush framing, what happens is the tributary area looks something kind of like this, that this girder is responsible for half of the load that, applied, or half of the distance, if you will, between him and his neighbor. So from here to here, so if this is, say this is 5 feet, if it's 5 feet between the beams, then this girder would be responsible for 2.5 feet here, and he would be responsible for 2.5 feet here. Okay, and so that gets us what we call our tributary width, and so I've shaded the tributary area associated with this girder. All right, so everything that's piled up here comes in, everything that's out in the middle comes in, and so you end up with a distributed load in KLF based off of this width. So I'll take my PSF number and multiply by that width, that tributary width value that we're talking about. Okay, now again, this is for non-flush framing. It means that the top of all members do not share a common plane. Only the beams, in this case, this is a beam or a girder, are used in supporting a slab weight and the area loads. And the girders do not directly carry any slab weight in this picture. Now let's compare that to our flush framing diagram, in which we have something that looks like this. Okay, for flush framing, the tops of all members share a common plane. Both girders and beams directly carry loads and the weights from the slabs. So here's the same structure, and now if it's flush framed, what happens is that rectangular area that we had for the non-flush framing now gets clipped a little bit, because any load that's showing up here, part of it comes down, but then part of it also goes over to the other girder. So you get this strange trapezoidal effect. So the question becomes, well, what's the dimensions of the trapezoid? And it's really easy. What's normally assumed in this is that trapezoid forms a 45-degree angle. Okay, so if I know this width is 2.5 feet, then I know that because of 45 degrees, that will be the same as that dimension there. It'll be the exact same 2.5 feet. So that's because of the 45-degree triangle on this, okay? And so once I have that, then that becomes the load diagram that would happen on this beam. All right, so let's go back and see what we can do with these kind of calculations. I'm going to step back to our non-flush framing first, okay? So we're looking at this particular picture, okay, in which it's a rectangular area. And you'll notice that the load diagram on these members looks a lot like the shape of the areas that we have. So keep this picture in mind as we're looking. Okay, so for that same beam, if you will, on here, the framing or the loading on that diagram for beam AB2, it's the same one we were talking about, would be, if we assume it's simply supported between the columns, I would get a reaction at the column at A and a reaction at the column at B, what I call is the left and the right. And again, it depends on your perspective and your orientation. Okay, and that the loading from that tributary area that was rectangular will result in a rectangular distributed load acting on this member. So here's the length of my beam, that's the distance between the two columns, and then here's the intensity of the load. Okay, and all we do to calculate that W is take the tributary width, okay, multiply it by the pressure. So if we look, so let's just say that this was an office live load. It had a pressure of 50 pounds per square foot and a tributary width of 5 feet. That's what we saw in the diagram. Okay, then the intensity of the load diagram on this guy, that one particular member, is going to be equal to then 50 pounds per square foot times 5 feet, okay, which would be 250 PLF. All right, once you have that diagram down, then we can come in and figure out, okay, well, what are the values of my reactions? This is now a statics problem, just like what you studied back in your basic mechanics classes. Okay, I've got a distributed load. I know my length of my span. Find the reactions. That's all it is. It's a classic statics problem. So at this point, we can leave behind and go back to what our basic skills are. Now, you could do sum of forces, sum of moments, that kind of stuff, or for simply supported, I can use a shortcut formula that says that RL and RR for this particular load case are exactly the same. And so if this beam is 20 feet long, as the diagram indicated, to find that reaction, I would take my new W, that 250 that's over here, multiply by 20, divide by 2, tells me that the reactions from that load for that beam end up being 2,500 pounds. Okay, and so we can kind of progress through. So we start with the secondary or the minor members first, because now we can go in and we can look at, well, what do I do about that girder that's on there? Okay, so the girder that we're looking at, if I come back and show you, is A23. And if I look at this, so here's column line A, and I'm looking for the girder that goes between here and here. Okay, and so what we're looking at is, well, what's the load that's acting on this guy? Now, the one that we just calculated was for here, and this is where you've got to kind of get some details figured out. Is, is this beam being carried by the girder, or is he framing typically into the column? Okay, and a lot of times these guys that are on the columns will go straight to the column and not load this girder, but it can make a big difference on this guy if the reaction is there. So if we look at this, and I look at my tributary areas, because this is regularly framed on here, and we are a little bit out of focus here. A little bit better. Sorry about that. Okay. All right. And so if we're looking at the girder that's here, then we can say that, this had a tributary width of 5 feet. That's what we saw. Well, if I look at the next guy down, well, he gets 2.5 here and 2.5 from his neighbor. He's the exact same load diagram as this one. And this one, same thing, 2.5 this way, 2.5 this way. And it's not until I get to that last one that I get something different. This guy out on the end of the building only gets half of what this one gets, because it's only 2.5 feet and he has nothing on the bottom side on those. So if we go back and we look and say that this is a non-flush framing system, okay, this girder then is picking up a reaction from this beam and is picking up a reaction from this beam, and we get a diagram that looks kind of like the following. Okay, so it's all about kind of tracing how these loads start to kind of work. Okay, so if we draw the girder for A23, then I get this beam, and I get the value of RL from the case that we did up here. We get this because that's his interaction. That girder is holding up this guy. And so when I do that, I get an RL that's directly at the end. I get an RL here, and I get another RL here, and another RL here. And then I know the spacings were all 5 feet. I know exactly where these point loads were acting. Okay? And so now we can start to kind of work our way through that. Now, notice that I had a full RL here. This was at column line 2. Okay, because it had 5 feet of width. Remember, there was another girder that took off over here. Okay, this one gets a 5 foot width, this one gets a 5 foot width, but this guy only gets half, because again, he's out at the edge of the building. That's column line 3. That was that bottom horizontal line on our framing diagram. There's only a half width, so this would be the loads that I would design this girder for. Now, again, even though these are acting at the column, I put them on the picture, but notice that this effect here will not cause a moment or a shear or anything internal in the beam because it's just going to go straight into the support. So whether I draw them or not doesn't affect the design of the beam. I generally like to put them on the picture just so that I know that I've considered it, so forth and so on. Okay, now let's take a look at, once you have this loading and we know the value was 2,500 pounds at each, it's now a statics problem. I can go find R2 and R3, the value of the load passing into the column from all of this framing, and you'll know that that load gets significantly larger. Okay, let's go take a look at girder B23. Okay, and so B23, here's line B, and 23 is the guy that's in the middle. He's the guy that's acting out here in the middle. So you'll notice that he picks up the right end of this one. So an RR here, an RR here, an RR here, and half of this one. But he also picks up the one from the other side. Okay, so he's going to be double. Well, in this case, double because my dimensions are the same. I think it's 20 feet for both spans. But if this were some different dimension than this, then the values coming in from each side would be different as well. Okay, so be careful of that. But all I'm going to do, I'm going to take the RR from this one and the RL from this one. Okay, and all of those will be the total that are applied here. Okay, and so when I look at my B23, your diagram looks something kind of like this. Okay, now I will warn you a little bit. I call everything an RR here. It's actually an RL plus an RR. So it's RL from one side, RR from the other. Okay, but because we made the assumption that they were equal spans and these values were equal, I did some algebraic cheating on this. Okay. And so the same effect is that I end up with 2 times RR plus 2 times RR plus 2 times RR plus 2 times a half R, which is why it's only a single. So notice there's no 1 or no 2 in front of this. It's only a single because, again, the girders that are coming in at column line 3 are only half the width of all of the others. And from this, now you can go in and you can analyze this beam. I can draw shear moment diagrams, and then you're ready for beam design once you get to that portion of your structuralist career. All right. Okay, so that's how we do a non-flush framing system. The flush framing system is a little bit different, okay? And so we're going to kind of work our way for what this diagram looks. So it's the same frame, it's the same structure, same loads. Everything is the same, except now we've changed how this thing is framed, and the diagrams change a little bit as a result of this. Okay, so for the flush framing, we talked about this 45 degrees that we had, so that's still the same. And so for beam AB2, instead of being what was a distributed load, which is what we had last time, kind of there, now it's clipped. Okay, so we know that the tributary width on this was 2.5 feet. So that means that if this is 45 degrees, I have for 2.5 feet, it goes from 0 at the support up to full W on this over a distance of 2.5 feet. And then I do the other end, 0 to full W over a distance of 2.5 feet. Again, that's because of that 45 degree rule that we talked about there. So if I have 2.5 feet here and 2.5 feet, it means I only have a full load W of 15 feet. So you can see that we've reduced the total load on this beam quite a bit because the girder that was happening here is helping to pick up the load, and the girder here is helping to pick up the load a little bit. So the load on the beam is actually reduced somewhat. Okay, and so if we go through and we do our calculations, okay, the tributary width is still 5 feet, and so the magnitude of the load is still 50 times 5. Okay, so that part doesn't change. The W is still the same. It's just the amount on which it's acting is different. And then I can go through and I can do my RL, RW, or left-right formula. Half of the total goes to each side. You can see that what was 2,500 pounds before is now 2,188 pounds acting on. So you've reduced the load fairly significantly. So, if you have a beam that's critical or that you're worried about, you can help take a load off of it by the way that you start to frame this. This will be a flush framing. One of the drawbacks of flush framing, though, is there's a lot more effort that goes into to putting all that together most of the time. Okay, there's generally more connections, there's more more bolts, or there's some extra additional welding that's needed. It's not just a gravity bearing type of connection as we saw on there. Okay, now so this guy, you've helped him out, but now let's go take a look at what's happened with these girders. Okay, so each of these girders we're going to look at. This girder will be the same as this one because the lengths are the same and the framing is regular. Okay, the girder, if we look at A23 on this one, has something really unusual start to happen to it. So that diagram looks like this. Okay, so for A23, so we get the point loads from the reactions, those RL values again. And again, those are smaller, but because that girder was contributing to picking up this load on here, that we have this ramp up, this triangle that starts to happen, develop in the middle of this thing. So over a distance of 5 feet from here to here, at the middle it peaks at 2.5. Again, that's that tributary width value associated with it. And then in between you get a little bit of extra load. And so you get these triangular patterns that form because the girder is now helping to carry a little bit of the W directly because of the framing positions. Okay, and so that's where these values are coming from. But again, it's a point load reaction from the beam sitting on the girder. That's what these are. And there's another one here and another one out at the end. And again, this guy is only half because he's out of column line 3. And then you get this extra triangle portion that shows up on the girder. So this is the extra that the girder has to carry. You've stolen a little bit of load in the point loads, but you've put it back on in the form of triangles and so forth and so on. So this girder will be a little bit bigger than the one from the non-flush system that we showed. So anyway, I hope that's made sense to you. I know it's kind of a short lesson for us today. When we get into some of the class exercises next time, we'll kind of show you some basic framing pictures and kind of look at some of the areas as we go through there. All right, so let's take a look at another one here. So here we have kind of a framing system. This one's a little bit more generic than the last one I showed you. Okay, but it's still a very similar layout. It's got column lines. Now notice they've switched the ABs and 1, 2, 3s, and that doesn't matter, you're labeling on that. But what I want to look at is kind of some of the nomenclature that the Casamali text will use and that you might come across in your explorations of this topic. Okay, when we did live load reductions, we talked a little bit about the different types of members that were associated with it. So this is kind of illustrating that these interior beams are considered to be these guys, the ones that are not near the edge of the building. And we normally distinguish them because the exteriors get different types of loads. You may get a torsional effect, or it gets half of the vertical load. It's a little bit of a different loading, but a lot of times with regular spacing, our interior beams work this way. So what we want to look at is, now this might be a typical floor framing plan for a particular structure, okay, as we start to look at it. But in this case, where we had equal dimensions last time, we now have unequal dimensions, presumably here, and we'll keep things kind of set up with L3s and L4s and going into this. All right, so to look at this beam, this interior beam here, is exactly what we did before. We take half of S1, half of S1, and that gets us our basic area. And so all of those work the same. The one out here at the exterior only gets half of S1. Okay, so we can look at that, and that's what we see on that picture there. So here's my half of S1, okay? And you can see S1 over 2 would be this shaded region. So this is in the packet if you need to look at that. Okay, let's go look at column line 2. Column line 2 is a little bit different because notice the spacings are different on either side of him. So what I do is I take half of his spacing on this side, and I take half of his spacing on the other side, and then I draw the tributary area associated with that. Okay, and so that's what we did here. And so here's S1 over 2, and here's S2 over 2, so forth and so on. And we can look at that. Okay, so the width, it doesn't have to be the same width on either side. It's literally half of what his neighbor contributes and half of what his neighbor contributes. And so S1 over 2 plus S2 over 2 gets me the width, and then I multiply that by the PSF, gets me the load that's acting on this guy. And so you can see that the loads here, assuming S1 is greater than S2, will typically be greater than the ones that are here. Okay, and so, but there's a transit, kind of this guy that's in the middle between one spacing and the next will be kind of an intermediate value between that. Okay. Now again, you don't have this problem if everything is the same spacing, but for this scenario. Okay, and then we can go back and we can look at our other interior beam on the other side is now S2 over 2 happening there. So hopefully that's made some sense. Okay, all right. But let's go take a look at then the girders. Okay, so we've got an edge girder happening here. He's holding up these beams here and here. Okay, now one way that we could go back and we could do that exact method that I showed you where you went through and put point loads on the girder and so forth, or we could kind of get kind of a rough feel for how much load on this by taking the tributary area associated with the girder. So just like the beams where I had my beam and I took half to his neighbor and half to his neighbor this way, the girders work the same way. If I just want to get kind of a sense of the magnitude of the load, it's not an exact, but it is kind of an approximate method to doing it, is that I can take half of the distance between this girder and his immediate neighbor, which is this guy down here. So the distance that he's responsible for is L3 over 2, and I could do a quick model of this as a distributed load of some magnitude based on the pounds per square foot load in the area multiplied by this distance of L3 over L2. And if I do that, then I don't do the point loads from this, because we just kind of smeared it and kind of taken an average value, if you will, on that. And that's a real common trick for analyzing this guy. Okay, same thing for an interior girder, such as this one. Okay, I take half of the area below, L4 over 2, and I take the half of the area above, L3 over 2, will get me that value. Okay, so the method I showed you before is what is more of an exact method, because you're tracing the loads through all the members through their point loads, but this is kind of an average effect, and this will get you close. You know, if you're doing a preliminary analysis, you just need a basic size to get started to investigate possibilities. That's one of the ways to do it. Okay, the last piece then has to do with columns, and columns are a little bit tricky as well. All right, so here we've got some columns, and we have a couple of different designations. Okay, the one out in the middle that has 4 regions on either side, we play the same kind of tributary game, right? I take half of the distance to his neighbor on the north, half of his distance to his neighbor on the east, half of his distance to the west, and half of his distance south, and that shaded region right there becomes the tributary area associated with this column. So I can play the same game. Okay, and again, this is just kind of an average value, not the true trace through values. And I can take the PSF multiplied by this area, and that will give me the load acting on this column, acting vertical. So that's an interior column. Okay, if I look at the column down here, this is what we call as an edge column. Okay, because it only has 2 regions. It's got the region on the northwest and the region on the northeast, assuming north is acting up. And then there's nothing down below because there's no building down below. And so you can see that different hash pattern that I have shown here is his area. But it's just the exact same process, that it's half of the width distance to his neighbor, half of the distance to his neighbor, and then half of his distance to his neighbor this way sets those areas. Okay, and those become our tributary areas. The last one then, this is what we call as a corner column, okay? Corner column A1, and just like the others, it goes half to his neighbor this way, half to his neighbor this way, and now you've got your area. So that's all there is to doing these tributary area calculations, being able to do it. And this is really handy for buildings that are multiple stories, as I can figure out the loads for this floor, and then if this framing duplicates for the next one up, you know, the next floor up, and for however many floors, I just take the values from one floor and multiply it by the number of floors above it, and I can quickly get an axial load in a column just using these basic tributary areas. So it's a little bit of a crude statics, if you will. It's mostly area methods, and it's not overly difficult, but it will get you a first guess at the values, and you can do it very, very quickly and very, very efficiently to get a sense of those. Now, again, this is not used for final design. You have to go back and do your due diligence and trace the loads around exactly on a final design. But if all I'm doing is trying to get a start or get a sense of the size of the numbers, this method is very, very convenient for doing so. So those are our tributary areas. So you notice that girders and beams and columns are all done a little bit differently. But if you've got the diagram, the framing diagram, it's real easy to start to figure out those areas. Okay, all right. So that leads us into then our class exercise, and of course I ramped this one up a little bit, and I'll talk a little bit about it and let you kind of work on it, and we'll talk about it next time. Is that what do you do about openings on here? Openings are a little bit different, okay, because now we're starting to cut some beams short. So like B1 here only goes from here to here, but now I've got a girder around this opening, because you have to frame an opening. Maybe there's a stairwell, or maybe it's an elevator shaft, or something, that there is framing that can redirect loads around this. And this is why you have to be a bit more precise when openings are involved. You know, I can't do that average value very well, because this column, if you thought about doing the half, would take half, comes down to here and over, and most of that area is open, doesn't have any load anyway. So we would be overestimating this load and stealing it from some of the other columns in the same bay. So we got to be kind of mindful. But you can still figure out that, well, what does this G1 look like? Well, if I assume it's simply supported here, and I assume it's simply supported here, then I would have 2 point loads coming in from these B1 beams, right? Okay, and then this guy would put a point load onto G2 at this location, and then this G2 gets half of the tributary width and distributed load plus a point load on that. And like I say, we'll talk about that next time in the next class. So openings can kind of muddle the process a little bit. It's not necessarily that difficult, but anytime you have a structure with an opening, you've got to be a little bit more exact. I mean, look at this bay. Okay, most of the load is gone because the opening is here, right? So this column gets next to no load on it. It does get a little bit from the other side over here, but from this bay here, there won't be a whole lot of load going into him. And this guy just gets a little bit, it's just a little sliver, whatever that dimension ends up being. Okay, so anyway, like I said, we'll talk about this more, in our next session, and we will go from there. So anyway, I hope that's made sense to you. The use of tributary area is very, very handy skill, and may have been the first time you've seen something like that. So I thought it would be worth spending a little bit of time to discuss. So anyway, as always, if you've got any questions in this video, please leave a comment down below. Let us know what we can do to make things better. And as always, happy engineering. We'll see you all next time. Thanks. Bye.